Chapter 7, Continuous Probability Distributions and the Normal Distribution. We're going to continue our discussion from the last lecture on Chapter 7. Just first, let's recap how we find area using Z-scores. We use the calculator's normal CDF function to find the area under the normal curve, which is the bell curve, between two Z-scores. So this is our bell curve, and hypothetically we're looking at a situation where we have a z-score of 0 and a z-score of 1.5. The area between a z-score of 0 and a z-score of 1.5 is this shaded portion right here. Now, when you're asked to do this on paper, you just want to make sure that 1.5 is somewhere to the right of 0. Okay? You don't have to be perfect with its placement. We know that the entire area under the bell curve is 100%. So the area under this piece, this shaded piece, which definitely is less than half of that, has to be less than 50%. So how do we calculate it exactly? It involves calculus, but the calculator has the function normal CDF to help us do this. So normal CDF, just to recap where you find it, you find normal CDF on the calculator. If you click second DISTR, normal CDF is number 2. There's a big difference between normal PDF and normal CDF. Normal CDF will be a cumulative distribution function which will basically accumulate area between two z-scores. So that's the one you want, number 2. So you go down to number 2 and you hit enter. And now you're asked for a lower z-score and upper z-score. You'll leave mean at 0 and standard deviation at 1 and then paste. So let me go back to our PowerPoint. Okay, in this case, the lower, which is always the z-score on the left, is 0. The upper, which is always the z-score on the right, the greater of the two z-scores, is 1.5. When finding the area between two z-scores, we are always going to use a mean of 0 because our z-score in the center is 0, and a standard deviation of 1. And then we'll scroll down to paste, and then you'd hit enter and get that answer. On this scenario, we're looking at a case where we start at a z-score of 0.67, but notice how the shaded area continues on all the way to the right, which signifies that this is being shaded towards positive infinity. So in that case, our lower z-score is 0.67 because that's the z-score on the left, and the right z-score we're going to use 100,000 to identify a number that's just very, very large to represent infinity. Again, our z-score, our center z-score is 0 and our standard deviation is 1. For this one we get 0.4332. So the proportion of area between a z-score of 0 and a z-score of 1.5 is 0.4332, and here we get 0.2514. The proportion of area from 0.67 to infinity. Okay. Okay, let's look at a scenario where instead of being given z-scores, we were given the area, and can we go back to figure out what the corresponding z-score is? And the calculator's got a function for this. It's called Imvnorm, standing for inverse normal. Normal CDF will take us from z-scores to area, and Imvnorm will take us from area back to z-scores. Okay, so what it does is we give it area as an input and it gives us a z-score. We find Imvnorm in the same location as we find normal CDF. Second DISTR, we're going to go to Imvnorm. But there is a catch with Imvnorm. It will only accept as input area to the left, and it will return the z-score that gives that area. So here's what we mean by that. Here's a scenario where the z-score is defined as z on the horizontal axis. Is an unknown z-score, but you're given the area to the left of that z-score as lower proportion of area is 0.2. So the lower 20% of this bell curve is shaded in. So if you have the area to the left, you can enter that area to the left, that 0.2, into Imvnorm, and it will provide to you the z-score that cuts off that area to the left. And in this example, we have an area that's shaded that's to the left of a z of 2.56. So if we put area to the left of z as, and the notation here says it's 0.9948. If we enter 0.9948 into our functions, into our calculator's Imvnorm function, we will get an answer of 2.56. So let's look at an example. For a normal distribution, find the z-score or scores that cuts off the lowest 20% of area, cuts off the bottom 20%. So basically, I'm going to show you on the calculator how you arrive at the answer from the previous slide. So we're going to go to our calculator, and we are going to find the Imvnorm function. So I'm going to quit normal CDF, which is I was at before, and Imvnorm second DISTR. Imvnorm is number 3. Hit enter. And it asks you for 3 things. The first is area, and I want you to remember that when it says area here, it really is expecting area to the left. Okay, so you may want to make a notation of that in your notes. This is area to the left. So if the area to the left in our particular problem is 20%, we're going to enter as a decimal 0.20 or 0.2. Okay, area will always be expressed as a decimal in Imvnorm. Now since we're dealing with z-scores again, we're going to let mu stay at 0, the center of the distribution is 0, and sigma stay at 1. Then we'll go to paste and hit enter. Now we're at the home screen and we hit enter one more time. Okay. Our z-score comes out to be negative 0.841621. Okay, we're going to round our z-scores to 2 decimal places, so this becomes negative 0.84. Now that should make sense to you. The reason why we get a negative z-score is because we're dealing with a z-score that's on the left side of 0. So let's take a look at our picture again. Knowing that 0 is here, and anything to the left of 0 has a negative z-score, and the z we're trying to find is here, it should make sense to you that z came out to be negative 0.84. Now, when you're asked for the lower proportion of area and you're told that it's 20%, you're basically being asked for the 20% on the left side of the bell curve, because the lower side of the bell curve is on the left and the upper side of the bell curve is on the right. So the bottom or the lower 20% is that piece of area 20%, lower 20% on the left. Okay, so our answer here is negative 0.84 when we expect a negative z-score. Let's look at another example. First, before we look at another example, let us remember that the bottom 20% is the same as the z-score that cuts off the top 80%. So if we look at this picture here, this piece of area that is shaded in is 20%, and this piece of area that's not shaded in is 80%, because we know the entire bell curve is 100%. So this z-score is the bottom, or rather cuts off the bottom 20% and cuts off the top 80%. It's the same z-score. So you should be able now to answer questions when the area to the right is given, because you simply subtract 100% or subtract from 100% to get the area to the left. So let's look at an example of that. The highest 10% of area. So this means cuts off the top 10% or 0.10 of the z-scores. So here's an example of what it looks like to be in the top 10%. This piece of area that's shaded in is the top 10%. The z-score that cuts off that top 10%, you should recognize, is the same z-score that cuts off the bottom 90%. Okay, the bottom 90% and the top 10% have the same z-score cutoff. So this piece in blue is 90%. And we have to remember that Imvnorm only takes area to the left. That's why finding that 90% is important. We can't do this problem without understanding that the area to the left is 90%. So when we go to Imvnorm, we enter the area, which is the area to the left of the z-score we want to find, as 0.9 or 0.90. Mean is 0, standard deviation is 1, and go down to paste. And before you hit enter, you should already recognize that you're expecting a positive z-score to come out of this, because this z-score is on the right side of 0. So we get a z-score when rounded to 2 decimal places. It's 1.28. Okay. Okay, one more question. We're going to find the z-score that cuts off the middle 90% of area. Okay. So the middle 90% of area, or the middle 90% of all the z-scores, looks like this. You've got z equals 0 in the center. You've got the first z-score, I'm going to label it as z sub 1 on the left-hand side, and the other z-score, z sub 2, on the right-hand side. In the center, the middle 90 looks like this. Because it's the middle 90, it's got exactly 45% of that to the left of 0 and 45% of that to the right of 0. So if we cut 90 in half, we have 45 and 45. So now we're asked for a z-score that, or rather 2 z-scores for which area is between them. 90% of area is between them. So we have to think a little bit outside the box and think, how can Imvnorm be used in this case? Because it's a little different from the previous cases. So remember that a z-score cannot be found unless we know the area to its left. So what is the area to the left of z1? Looking at this image, knowing that the entire bell curve is 100%, this piece of the bell curve is 90, so the remaining tails, the empty tails that are not shaded in white here, make up 10% total. So the area in this white tail on the left, you should recognize as 5%. So if the area right there is 5%, the z-score here can be found because the z-score basically cuts off the bottom 5% of the bell curve. So we go to Imvnorm and we put in 0.05. It's very easy to make the mistake of putting in 0.5 or 0.005 if you don't understand your percents. 5% is expressed as a decimal, 0.05. We put in our mean of 0, our standard deviation of 1, and then we hit paste, and we get a z-score of negative 1.64. Okay, negative 1.64. Now we would expect our z-score to be negative because it's on the left side of 0. Okay, on the other side, z2, there's a couple of ways that we can find z2. We can recognize that the bell curve is perfectly symmetrical with respect to this line at z equals 0. So if this is negative 1.64, z2 has to be a positive 1.64. But if you want to show how we can do this on the calculator, recognize that Z2 has 95% of area on its left. So if you go to the calculator and you put in 0.95 as the area to the left, so we're in Imvnorm, we're going to put in 0.95 as area to the left. Mu stays at 0, sigma 1, paste. We get a positive 1.64. Okay.